Yeah, so for this week's AI seminar, we're joined by Nathan Lambert. He's a senior research scientist and post-training lead at the Allen Institute for AI, working on open language models. He also founded the blog and podcast Interconnects AI about new developments in AI. And he received his PhD from UC Berkeley in machine learning and robotics and helped build a RLHF team at Hugging Face before he worked with the Allen Institute. So for questions, I think Nathan said we can ask like clarifying questions during the talk and maybe save some of the open-ended questions towards the end. And with that, I'll hand things over to Nathan for his talk. So thank you.
Yeah, thanks for the introduction and inviting me, and I will talk to some of you through the day. It's a nice way for me to get new ideas into my ecosystem, and mostly going to be talking about what we've called reinforcement learning with verifiable rewards and do some of the reflections on how we got here through ChatGPT to RLHF to post-training to now RL is a big thing in a much more direct way. I have a lot of material. I think I'm definitely going to try to make time for questions. So if I start going fast, I will give you fair warning on I'm speeding up and we can revisit things if they were of interest to people. So a thing that I've been talking a lot, starting multiple of my RL talks with is this screenshot of this paper on TD gammon, which is a Tesoro et al. Paper from the 1990s, which solved backgammon with reinforcement learning and neural networks. I think mostly it's a nice reflection on where we came from. They use things that are very popular today. I think self-play is not as in favor, but it was crucial to getting RL where it is with AlphaGo and all of those successes. And it reached expert level performance in a game or a task, and it used neural networks to learn a value function. I think a lot of this has not changed, yet we have gone through history, and what it actually looks like is very different at an implementation level, and the things we're doing are very different. So the next question is like when we're leading into this RL fine tuning, it's like where did RLHF, reinforced learning from human feedback, actually come from? Here is a link to a good paper to think about if you're trying to actually trace this history, which is a bunch of the core people in RLHF when they were at DeepMind, kind of proposing reward modeling as a research direction. And this is a position paper on reward modeling being able to capture interesting behaviors in humans and complex complex kind of values and so on. And it has one of these first kind of RLHF system diagrams that will kind of go through where there's an agent that interacts with the environment and there's feedback that comes from a user, and these together create a reward model, which is the thing that the agent is then optimizing. And in this is very new. 7 years is not a long time compared to a lot of the things that we're looking at in RL. But these diagrams kind of very much so evolved from here, with subsets of these authors being on lots of the seminal papers for RLHF. How I view RLHF relative to the current boom of RL is going to be something I bring up in this talk at multiple times. I think I see it kind of as a precursor and also a catalyst for what's going on in the new hype behind RL. It's good to ground in this sentence from the ChatGPT blog post, which is that they train the model using reinforcement learning from human feedback with same and improved methods from InstructGPT. And the way to think about this is RLHF was necessary but not sufficient for models like ChatGPT, and we don't need to go on through all the uses of RLHF from here. But RLHF has been very necessary. It's been scapegoated at times, but there's been no getting away from it ever since this moment as something that leading AI models are, at least most of them are using or considering or need to have a strong reason to do something else. And here comes this great meme that I like to use in a couple of my talks. I did not make it. You can see the credit, which is that RLHF was really important to a lot of modern models. It's what laid the groundwork for how we use these models with this kind of chat interaction mode. It's very foundational there. And it kickstarted this renewed interest in language models and really like RL and language models. So a lot of the infrastructure that we use now when we're doing RL with verifiable rewards is all downstream of pretty bleak years in the open source and academic community in terms of trying to do any RL on language models. And there's the story of DPO and all these things that I don't go into in full detail of this talk. But these stories and how the different eras of post-training and things that people are doing to fine-tune language models interweave in very interesting ways that I don't think get quite enough credit. And in some of my talks now, I'm trying to actually push people to keep working on RLHF and not just do this RL for verifiable rewards, which is that RLHF is far more messy and interdisciplinary, and I think has a longer term kind of academic outlook on just foundational problems that we can't solve, but we need to do the best that we can. Whereas RLVR and this reinforced learning with verifiable rewards that I will explain is like so simple in its goals to make the scores better and the models just higher performance on tasks that we care about, which is very aligned with industry. And it makes sense that they would do this as they're trying to deliver value to customers. But I think in not this year, because when things are hot, you have to do them. But spending more time on RLHF is very warranted, and do not kind of short sell it during all of this excitement about how this new type of RL is far easier and we don't have to collect preference data and do all of these very hard things. And a lot of people will say that this, like these O1 moments in scaling RL came out of nowhere, but there are really multiple trends that came together at once for this to happen. There's a lot of literature before O1 was released on using this kind of verifiable outcome rewards, whether a math problem is correct or a code snippet is correct, and so on, to improve language models on those domains. So the core ideas, and I think this is something you see in deep learning and RL countless times, is that these ideas are around, and then a lot of the major breakthroughs are about scaling it up or applying it in the right way, or just kind of being confident enough in an approach to kind of go all in on it and see what the limits are. And that's kind of where like O1 is the paradigm shift that makes RL research something that more academics are interested in and flooding to, which kind of has these ecosystem effects where all the little knowledge points are much more distributed across the community and progress just accelerates. So O1 was this model that most people know that can reason by this training from large-scale reinforcement learning. There's a plot like this, which is the ArcAGI abstract reasoning corpus, the scores plotted on OpenAI's models by release date. And this is the sort of thing that happens when a new training paradigm and a new focus on how to use the models comes about. And the downstream of this is that everybody is interested in RL, and there's just a lot of digging in it, which is great for learning more. So this is kind of the core of the talk, is going to be kind of a light intro to post-training, but mostly is like, what does people actually do research on when they're looking at this new types of RL training, and what are trade-offs in relations to other topics, and some common phrasings that you'll hear in the news. In order to do this well, having some basics and terminology for post-training will really help. I already threw a bunch of words at you in the intro, and we'll kind of ground them in some more reality before we go forward. So post-training, especially at the Allen Institute, we use the kind of neutral term adaptation of language models. Is we take these raw pre-trained base models, which are fairly unpredictable. It's a very good exercise to go talk to base models. I still do it more. You just are grappling more with the kind of underlying, I don't want to say necessarily capabilities, but behaviors that come when you just do this internet scale pre-training is much more spiky and much more random. And in post-training, we are taking that underlying capability and shaping it into something that is very useful for users. So following instructions, safety can be something that's often done more in post-training than pre-training. Human preferences, core skills like math, coding, and whatever the latest things are, like tool use and agents. And historically, post-training actually was almost equivalent to RLHF. So some of the early papers on reinforcement learning from human feedback, like InstructGPT, had used these terminologies like a 3-stage pipeline where you do instruction tuning and then reward modeling, and then you optimize it with RL. You could put system diagrams together for this, which are fairly simple. And today, if you look at modern papers like Llama, Nematron, Tülu 3, it is very complicated, with model versions being passed along at different versions, and human preference data and synthetic preference data. And if you were to talk to labs, it would probably be like OpenAI, it would probably be even more complicated than this, with different improvements getting folded in at different model versions. So modern post-training is a very complicated multi-stage process that grew out of what was once a recipe just to do this reinforced learning from human feedback, where the human preference data was really core to kind of doing this. It's now one part of a much bigger system. The way that we describe it in Tülu 3 is that we kind of have three different objectives for post-training, as in algorithmic objectives or training objectives. And each of these objectives is doing a different thing to the model. So depending on the goals that we have, I think we can start with supervised fine-tuning, which is really the foundation of post-training, which is we're teaching formatting and generally like how the model should respond and the shape of the response. And a common word that you hear for supervised fine-tuning, which is still using the autoregressive loss function that's done at pre-training, is that you're teaching features to the model. So if you have common phrasing, like I think at one point Claude said certainly a lot, I would guess that a lot of the instructions that were given, either if they were generated for humans or modified by an AI, just would have that sort of feature in the data extensively. And then as we get to the two other types of loss functions, they're much more open-ended and harder to interpret as literal changes to the model behavior. So supervised fine-tuning is very much teaching the model like what types of tokens should come next, where preference tuning and reinforcement fine-tuning are much more like trying to capture more nuanced signals. So preference fine-tuning is the closest analog to reinforced learning from human feedback. It's mostly a generalized version, so we can include algorithms like direct preference optimization and so on. But most of them boil down to taking some sort of comparison data and say, be more like one thing and less like another. And when you take tons of these samples, it's really nuanced to say exactly what is happening from being more like some things and less like others. But what it has is it really helps style, and it can also help other abilities like math and code, which could be from just teaching the model which types of reasoning behaviors or which types of chain of thoughts to look a bit more closely like. And in many ways, this spectrum, as we go through these three loss functions, is like a continuous spectrum, because then reinforcement fine-tuning is the most open-ended in which types of behaviors it can have emerge from it, where the model is sort of searching over different completions and rewarding certain completions for being successful in solving a task. And this is the one that we'll spend most of the time on. And it's like, I subscribe to the elicitation view of post-training, which is at pre-training, most of these behaviors exist. They might just be such low probabilities that we can't really extract them as a user. And in post-training, especially with this new RL training, we're trying to get the model to try a bunch of behaviors and then really quickly upweight the probability of behaviors that is useful for solving tasks that we care about. So if we go back all the way to kind of RL basics, it's like we have an agent and we have an environment. An agent will take actions in an environment, and the environment will return a next state and a reward. With language, this becomes much messier. The language model, it becomes the agent, which means the prompt is a state and the action is a completion. And the environment is the most contrived part, where the environment doesn't really exist. I think an extension we want to get to, which is where the user is actually the environment in the training process. But because all of these are really just trained in a single turn manner, or most of them are, what happens is that we don't really have an environment. We just have a reward function. And you just have a next state, which is a new prompt, which is really not related in the history. So you can get something that's much closer to this, which is just that the prompt is used once and there is no real environment. It's mostly just an agent interacting with prompts and getting some sort of score. And if we want to transform what is considered like standard RLHF into this reinforcement learning with verifiable rewards, we need to kind of think about like how we would substitute a reward model for a basic question. I think the idea that most of us started with is let's add the verification function to the reward model, but it turns out to be fairly simple that you don't need to do this. So if we zoom in on what RL would look like, especially using, it depends on the algorithm we'll use. We'll talk about some of those trade-offs later, but inside the agent, when you're doing fine-tuning with a language models today, there's a bunch of other models that are under the hood. There's this generating policy, a reference policy to make sure you don't change the model too much, and sometimes a value model. for the purposes of this talk and making it accessible, I mostly ignore a lot of these details, and we just kind of think about this. And what we need to do is swap out the reward model. And all we've done is we've changed what used to be a reward model of human preferences, and now it's some sort of a scoring function, where a positive score is given if the answer is right, and no score is given otherwise. That's really kind of a fundamental idea in RL, and I'll kind of talk about those connections a bit later on. And then there's a lot of ways to verify these rewards in practice. I think there's open source libraries like Math Verify. A lot of people have their own internal version of this, which is checking what they like checking the formatting of the answer. There's a lot of hints in the literature, such as using like LM as a judge to check if factual knowledge is right, which is a bit of a softer verification. Code sandboxes to check unit tests, which are something that we're spinning up, which is mostly just it's exactly similar in idea, but much harder to implement in practice because you have to have different processes to run code and worry about safety. But this idea of a ground truth reward can be expanded to many different domains, and that's what a lot of ongoing research is right now. To kind of keep zooming in, it's good to just, if you're getting started in this area, to just go look at the training data that's actually being used. An example here is one of our Hugging Face data sets for instruction following. And all of these data sets need to contain a prompt and an answer. And what you do is you take the prompt, you pass it to the language model, it generates a completion, and the completion is checked to see if it has this answer. So the prompt on the screen I just showed you is describe the purpose of Internet Protocol version 6, IPv6. Your entire response should be in English and all lowercase letters, no capital letters allowed. So the answer checking function in this case is going to be like check is lowercase. And that's something you can apply with, it makes more sense as like just kind of generating text. It is more complicated than math, but math problems are also very simple. I think you could see is this multiplication problem, and then you have to check if the answer is whatever that number is. I don't need to read it all out. I think the nuance comes in, which is where you have many ways that you can express the same quantities. I think there's an example for math problems here where I've given 5 different ways that you can express the same number. And this largely shapes back to OpenAI had announced that they were going to have a reinforcement fine-tuning API, and they released some details about their grader models, which was really interesting. The API has not yet been released, but the idea is that the grader models, when you get into multi-domain problems and much more complicated problems than basic like arithmetic or closed like GSM8K or math problems, is that you need more ways to shape your reward and weight different problems and different answers within the same problem. So this is where reward shaping from the RL literature really starts to come into what people are doing with this fine-tuning today. And there hasn't been a ton of literature in it, and our work hasn't really touched it that much. I'll talk about a few domains that we're working on, but it's mostly we're pushing on per domain. And then when you're trying to integrate more domains at once, these kind of ideas of how you weight different problems and different intermediate solutions are going to become very important. Okay, so I'm going to kind of pause, and now I'm going to kind of talk about many different things that we've done with this framework. I'm probably going faster than I need to be or I would have expected, so we should have time at the end. There's a lot of different categories of ways that people are using these RLVR or generalized like scaled reinforcement learning for language models today. The way that we came to it was within general post-training, which is after doing instruction tuning and preference tuning, we did this RL stage at the end in order to boost kind of key capabilities that were hardest to raise in the other stages, like math, or math is really the focus for our previous work, and then we're going to move more into code. The way that most people actually heard about this is through DeepSeek's release and the combination of that with OpenAI's O1, where they do very large-scale RL on a base model directly. And generally, this is not too surprising, but you just have to think about the type of behavior change you would want from a base model versus an instruction-tuned model. If you've already gone through a lot of post-training in RLHF, you probably don't want the model to change as much with RL. Whereas based model RL, you want the model to change a ton and learn these dramatic chain of thought behaviors, and then you do the preference tuning later on. And then there's kind of a lot of ideas on like how do we actually expand this research that's starting on math and code to more things. There's a lot of interesting research that's starting on tool use, such as RL for RAG and RL for search that I haven't really touched on, but it's nice because these tools link almost more nicely in the conceptual framework of RL, where like a tool is a pretty closed form action rather than just looking at if the whole completion was right and moving more into multi-agent or like multi-step and multi-action sequences for these RL algorithms. If you come from an RL background and you start doing language model RL in this new format with RLVR, these curves look remarkably similar to standard practice RL. I think this is one of our first reactions when we started doing this is like, wow, this is actually easier than we would have expected. On the screen here from left to right is the KL distance and then two different ways of representing the reward. One of them has a KL penalty in the middle and then on the right does not. And these four lines are sweeping over just different levels of the KL penalty beta from 0.1 to 0.001. And while the left plot is how much the model changes, it doesn't really matter, and the actual performance gains are somewhat similar. But even just having nice stable curves like this over sweeps makes doing research far easier. But when we transition from that sort of slide where things look pretty simple, is that there's a lot of weird things you can do with this. So right after Tülu 3, we're releasing our OLMo 2 models and just trying to get the most performance we can out of the training stages we have. And the thing we did was we started running this. The blue line is our first run of all RLVR. So we ended on our DPO trained model. We plugged it in, scores go up. And then it's a simple idea of like, what if we just restart the same RL? We're training on the same prompts, but we start from a different base model. Instead of the DPO model, it's a model that has been trained with a bit of RL, and the scores go up again. So we just kind of did this iterative RLVR to get our final models, and the scores were going up. I think largely these are exploratory and not rigorous, but go to show that there's just a lot of opportunity for kind of quick gains depending on your base model and stuff like this, which compared to some other areas that we have worked in is definitely not always the case in post-training research. To put all the numbers in perspective, the RL gains relative to kind of SFT and DPO have still been relatively low. I would say that I expect these sorts of per stages to the scores to change dramatically throughout the year as people figure out the right data to train with RL. I think for some of these models, I can say like the OLMo 2s, we've already trained better models with RL checkmates that are released in the paper. And it's just kind of another sign of quick gaining slopes. But one of the more interesting questions will be if the kind of standalone preference tuning stages still train and how you actually sequence these. We sequence these in 3 stages, mostly because of convenience, but it might be that things, as you go more of I showed the figure in the beginning of like what llama or these complicated recipes look like. It might be that you need to change loss functions multiple times in this post-training recipe, and you can kind of keep hill climbing on your evals. And I mean, I think just to kind of dig into this, you can see that it's kind of random, the magnitude of gains that we get. Like sometimes the final RL model is about the same as DPO, but sometimes we get like 2 points on average. And I don't have an intuition for when that happens or doesn't. I would add that a lot, especially I don't even need to say in just industry now, but there's a lot of discussions on how RL is very variable across seeds. And for example, in industry, they would do something where they start many RL runs at once, and then they look at the early learning curves and kill the ones that are worse and let the best few continue. And in our experiments here, we are probably running on top of the DPO checkpoint anywhere from 2 to 5 seeds, and we're normally letting it run for 1 to 2 days, where we could be increasing this and letting it run far longer because the amount of time into the run in terms of just amount of RL done is not constant for these models. So each of these instruct checkpoints, I have the OLMos and the final RLVR numbers for Tülu, come at different points on the x-axis in order of number of RL steps. And sometimes really late in the RL checkpoint, you get a better model. So a lot of this is just that if you let it cook longer, we could probably get better models, but it's really hard to know the return on investment in those GPUs and kind of swimming around in the dark. So that's my reflection on these numbers, and that's a hard thing to translate to research because you tend to have you have fewer resources when you're doing open-ended research, but these RL stages relative to SFT and DPO, I think, have much more variance in when you get the gains and how easy to predict it is. For example, SFT and DPO, I would say both have about 1 point variation from random seed, and we've known that you can do a learning rate sweep of about we'd probably do 4 to 8 learning rates, and then we do 1 to 2 additional seeds at the best learning rate in order to get that extra half a point at SFT or DPO stage. So RL is much more variable in terms of the actual numbers we get out, and one of the things I want to know is just how do we make this process more reliable and get the 2-point gains rather than just shifting to the more important eval scores. Another rabbit hole that I am personally going down and also the community is very interested in is this algorithm of group relative policy optimization, GRPO. GRPO is the algorithm that DeepSeek proposed in their DeepSeek math paper and that they used in DeepSeek R1, their large-scale RL paper. Going into this algorithm and some of the recent work I'll comment on is really great from a pedagogical or self-learning perspective on understanding the role of RL algorithms and how it integrates to infrastructure, how it relates to your model that you're starting with, and kind of how much gains you expect by changing algorithms, and broadly bigger trends in the tools used in industry standards. So I think the biggest takeaway from GRPO is another endorsement of the fact that value functions used to predict kind of a per token value rather than just an outcome value are increasingly being used less across the AI industry for any type of RL, both that preference tuning and this outcome-based verifiable rewards. And if you look at the loss function here, I've broken down a few things that we'll talk about in more detail. The middle in the blue, GRPO is a very, very close relative to PPO, this proximal policy optimization, which is probably the longest standing, most successful RL algorithm in its robustness and applicability to many tasks. 2 minor changes in the yellow and the red. The red is the KL penalty for GRPO is in the loss function, where in a lot of historical literature and RLHF, the KL penalty was in the reward. It's a minor change. It's like one of these implementation changes that is a trade-off that you don't know what you're going to get. And I'll talk to you about this yellow term, the token length normalization. So in a sequence, a completion to an answer, which is one of these G's in the equation, the number of tokens is this kind of, or O is each token. And when you implement this, the loss is per token, which is why you need to sum over from each of these O's in this equation. I feel silly talking about G's and O's, but you have to do, when you implement it, you do a per token loss. And the final thing to know about GRPO is that the advantage is just the how good the answer was relative to other answers to the same question. And that's what this is kind of scaling on the bottom, the specific completion that the model made in this RL step relative to the others in that batch. So what people are doing is discussing on is GRPO the answer to all of our problems? Is it just better? And a lot of these research questions are how can we better align GRPO to the reasoning style of training that we're doing now? So there's a couple of papers on this. One of them is DAPO, which stands for Dynamic Sampling Policy Optimization. And you can see here that the equations look really similar. What I'll focus on is in front of this double sum, which is a change in the normalization of the loss, kind of based on this G, which is the number of samples per prompt. So you ask one question and you collect multiple answers, and then you use that to compute your advantage, and this normalization of how many tokens are in each of those responses. The other paper was proposed an algorithm that's called Dr. GRPO, where essentially from the top to the bottom, they've removed these things in red, where they've removed this length normalization, saying that it helps with token efficiency and helps the model learn better, and they've removed this standard deviation. I will explain the standard deviation now because it's interesting and a good lesson where essentially what this advantage is doing, if we think about a case where all of the questions were correct in the batch, essentially your advantage would be 0. So all of the rewards would be 1, the reward of any sample would be 1, and then the mean of these is 1, so the advantage is 0, so there's nothing to learn from that sample. And the same could be seen if all the answers were wrong. But if you have something in the middle where some are right and some are wrong, the questions that are right will have a positive advantage where the reward would be 1 and the mean would be something like 0.5. And what's happening in this case is there's going to be a higher standard deviation between the rewards in that batch. Some of them would be 1 and some of them would be 0. So the standard deviation would be higher. So then essentially that would mean that it's a smaller learning signal. So you're dividing by that standard deviation. What the authors of Dr. GRPO say is we shouldn't be doing that. And they're saying that this is kind of changing the weights of different questions. But in reality, there's kind of no free lunch because yes, removing that helps the questions in the middle of your advantage distribution go faster. But if there's a question that is really, really hard, so it's mostly wrong, but just one right answer, that one, because it has a lower standard deviation, is actually going to be published by Dr. GRPO. So they're kind of fiddling to something, and it sounds intuitive when you describe it one way, but there are often a lot of side effects when you change the algorithm. And we've implemented this, and I'll show a comparison later, and it doesn't have a big effect. But I largely interpret these changes as depending on your data, there's definitely conditions where your data needs this change, but it won't actually always help you. And this is kind of going back to the other change of this one other O with the length bias. And length bias is deeply tied to the implementation of these algorithms. When you implement a RL algorithm with a language model, the loss is always computed per token. And you have a batch that has a bunch of sequences of different lengths per each question. And then you have these advantages and things like this. And it's a very tricky intuition, and I won't go into all the policy gradient math, but essentially you're multiplying a policy ratio times an advantage. So the advantage number is very important for your loss updates along with the actual probabilities. And most of these intuitions are based on the fact that from a language model, a very long sequence is less likely because you have a lot of low probability. You need to generate more tokens. If you just think about a probability distribution, it's like more low numbers that are kind of getting multiplied together. So it's less likely to end up with a really long sequence than a short sequence, at least when you start with these models. And what happens if you're doing this per token loss is that a low probability event will have a smaller weight in the policy gradient. And these intuitions are manipulating these weights based on length. So you can end up with a lot of different ways of changing the length bias of your algorithm, where the default GRPO has this 1/O term per sequence, which is understandably biased in length. I think you should go look at these papers if you want to understand more of the intuitions. But it's really kind of a trade-off between bias instability in practice, where this one over length term in the default GRPO, which is also used in most PPO implementations, is kind of something that people added out of convenience. It's very logical. It's like if I'm adding a loss per token over a number of tokens, if I'm just adding loss, it makes sense that I might divide by the number of elements that I'm adding over. It's kind of a logical thing. It's not in the derivation, but it's a thing that's been accepted in practice to be fairly stable, where these new algorithms are moving those, either trying to reduce the bias in practice, or Dr. GRPO, this final one, actually derives it and shows that the length is not in the derivation if you go from first principles of a per token loss. So I generally think that reacting to these papers is good for lessons, but it'll depend on your setup on which ones actually matter or don't. Like for example, in our setup, we added Dr. GRPO and did some runs. So blue is our default and red is our Dr. GRPO. And it's like, I know we don't really see any big difference. We still have the same problems, which is some of the runs blow up. We're not getting a ton more reward. We're not getting a big change in sequence length. So it's like, it's easy to be distracted on these papers, but mostly take them as a fun way to learn about the algorithms. And if you look at DeepRL's past, there's a lot of times where new algorithms are proposed which have a few percent in performance improvement on evaluations, but that's largely because they implemented it better and not because the algorithms are 100% better. It's a trade-off on what types of behaviors you need in your use case. And I will say many times that the implementation and the data that it's interacting with is very much more important than some of these subtle differences. I've gone down this rabbit hole in much greater length than I did here, and it has many different forms. I write documents or blog posts or recorded another talk just about these kind of implementation details and has links to, for example, the like different loss functions used across different code bases if you are interested. I'll be sharing the links to these slides with you. I can send it once I open the chat. I just don't need to derail what I'm doing now. So those are all ready to be shared. With this whole GRPO distraction, we did try this, and we did get some models that were much better with GRPO relative to PPO, but I think that it's more of what I said with being unsure on how to control the variance across our experiments and seeds rather than the algorithm being just much more useful. But these gains are just really big. So we go from like our Tülu 3 to what we call Tülu 3.1, and we gain very substantially on lots of evals that we care about. And it's just kind of like, it sometimes feels like digging around in the dark, and it's hard to get this coalescing function. And it's a thing that we're working on now is how do we pull all these research results that we have for RLVR, I'm starting to get into them, into like one model that's really easy to package and one code base that is easy for people to build on and get reliable results in their domain. So for example, I showed this table earlier of results. If you compare the results of this model, which was just changing from PPO to GRPO, it's like, okay, we got a much bigger step in our numbers with RL, but it's like, okay, we need to keep going to really understand why and the best practices for doing so. The places we're taking this now is kind of adding more domains and making the recipe just more fleshed out with RL. I think something that I have not talked about at all in this talk is the idea of inference time scaling. And if you want to do post-training well in a numerical eval sense, you need to be doing some level of inference time scaling because you're leaving performance on the table. I think RL is the most popular way to, I'll say this again in another slide, but RL is the most popular way to do inference time scaling. And we're experimenting with this approach from what was called L1 for length control, just to get the model to use more tokens to improve scores. I think in industry, we see a lot of kind of reasoning on and off, which I think could be a nice UX to have show how to do it in an open model. So that's kind of another thing we're thinking about is this balance between length control and then just can you turn reasoning on and off in one instruction tuning recipe. At the same time, we've made more progress on post-trained models, which are the instruct models, and experimenting with base models is very doable. I think it takes a bit of tuning, but it's not hard to get the results where you see some level of sequence length increase and some level of kind of accuracy increase on a base model. But understanding why it emerges, like if you need to do a different pre-training or a different mid-training is some of the more interesting questions that we're looking at, which is like, what are the behaviors that need to be in reasoning data in your pre-train or in your SFT in order to let the models learn much more and have a higher ceiling rather than being locked into kind of a certain type of chain of thought. An example that I'm very excited about, but won't talk too much of the details on, is that you can, for example, take a base model and just ask it multiplication tables. So I gave this example earlier with a kind of like 5-digit by 5-digit multiplication. And if you ask a reasonable language model like Qwen 2.5 math, it can learn this very large multiplication table, which a lot of people thought that language models just can't do this large scale multiplication. So you can teach them this, but also if you look at the downstream evals like math and Amy and all of these things, training on multiplication tables results in a model that does better on most of these math benchmarks that people care about, which is a very interesting and a half-baked result on just like chain of thought being I think more intrinsic to the models than people give it credit for. And in many ways, the training is not too special. We're also working on trying to move outside of these verifiable rewards, but is very messy, and putting the pieces together I expect to be somewhat hard. But essentially, if you think about verifiable rewards as math and code, you can think about something like a factual domain of being somewhat in the middle between standard preference tuning and RLVR, where you can have an answer checker, whether it's a smarter language model or something like this. And there's kind of actually a spectrum of verifiability on all of these post-training prompts that we have. And bringing this RLVR approach mentally to kind of like every instance that we have in our post training is what we're thinking about now, but scaling that and making it a full recipe is still months down the line. I think that I don't know the full audience here, but maybe people will ask questions. If you come from an RL background, RLVR sounds pretty silly because we're essentially saying we like figured out RL again and applied it to a language model and coined it as its own thing. But in reality, it's kind of the story that I started with, which is the remarkable thing is that it's accessible and works in a lot of different ways that I've talked about, and that it doesn't take that much fiddling. And therefore, it's like a whole new area of doing research. And it's not that we're trying to say that we're reinventing RL and like having a reward when the agent does the right thing is a new idea or anything like that. And particularly without degradation of out-of-domain capabilities. So when you do RLVR in a Tülu recipe, things like alpaca eval don't really go down very much, which is that these models just have a lot of capacity to learn, and we can add to them without cost. I think I would have thought that there would have been much more cost to doing this than there has been seen in any of these experiments. This is where I need to make the note of, this is the plot that OpenAI showed on inference time scaling. And RL is the most popular tool to do inference time scaling right now. But in the future, I think you can do research on one or the other, and there will be more ways of doing inference time compute that also improve performance. It'd be very interesting to see how it evolves, where either parallel generation and other techniques, and eventually it'll probably be that you actually don't want to increase the sequence length infinitely with your RL, because there will be more efficient trade-offs in getting performance with inference time compute. But that's a fun thing that we'll see emerge over time, and it's fun to just we'll see where it goes. I think I don't need to say too much on it. I think if you want to have a nice lesson on the parallel compute option, the Claude 3.7 release had a nice blog post on why they thought about parallel compute and didn't yet use it. I didn't include the link, but if you want it, I can send it to you. You can email me. I think the provocation that I want to end with, which is, what if this kind of RL type of training can be the focal point of language model development? I think for a while, it's like we've seen this benchmark improvement, but that's only like one side of the story. I think for a while sorry, I'm mispredicting my slides. It's okay. Well, let's see that the RL is being used for far more things I talked about. I kind of hinted at this with the tool use. I think we know that both OpenAI Deep Research and OpenAI's operator are trained with RL. We don't know the details. I think they're probably very good areas to work on things like this because they're much less saturated than math and code. And if we see this and the number of domains that we're training on expands far outside what we're talking about right now, it's like, how can this post-training idea just be the core of training, where we just have a lot of different verifiers in our RL environments that the agents need to act in and get training data from, and kind of scale up the compute and see where the trends are going with the reasoning training, especially with more inference. And it's like, is there kind of a shifting sand in where compute is used across the language model landscape? The point that I actually look at, which is based off a tweet, but if you look at the DeepSeek transition from the DeepSeek v3 paper, they use like 0.2% of their compute on post-training. And then tweets that the team members have said is that their DeepSeek R1 RL training took like a few weeks, which is way higher than this compute chart here. And I think that this is, we know the excitement in this from OpenAI and others that are scaling this compute. And the idea is, how far can this go? Can it ever be that post-training is like proportional to pre-training if you add in robotics and other really like token intensive action domains? It would be very fun. I don't necessarily expect it to happen, but it could motivate interesting projects on like, what if they are doing very multi-domain RL training, and therefore you need to do kind of off-policy RLVR and take data from many different models in order to improve one kind of core agentic model. I think it would be a fun outcome, but it is not yet high priority, and people, even though scaling is dead, it's still a very important thing for pre-training to use a ton of compute. These lessons and experiments are based on many people. I gave some direct shout outs on the slides for people where I'm kind of just taking their experiments they ran and pasted them on a slide, but many more people contribute to these intuitions and ideas. So it's a fun time to be an RL researcher, and I will take questions and talk to some of you throughout the day. But thanks for having me and taking the time to listen.
Yeah, I think people can, unmute themselves more or less, but if anyone wants to like raise their hand, or we can call on them too. I don't know.
There's
I see raised hand, sorry.
There's questions in the Q&A.
Oh, in the
Okay.
Q&A.
I'm gonna stop sharing so that I can look at some of the stuff more, or I don't know if I have the Q&A. I think I don't.
I'm not sure where the Q&A is either.
I'll start with the Q&A. Were you able to share the slide deck after the talk?
Oh yeah, let me find this. I'm clicking around. I am. Where is my Zoom? Okay. Okay. But yeah, I can also put this in email so that it's more permanent. I'll do that.
And the second question, go ahead, Christina.
Hi. I was going to ask a question. You spoke about spectrum verifiability, but in human domain, social domain, which is most interesting domain, at least in my mind, you cannot verify. There's subjective answers, and they might conflict between different types of people, maybe different types of groups. If you ask liberals if wearing masks during epidemic is good, they'll say yes. Conservatives will say no. So how can you create reward signals that might capture that kind of subjectivity and disparities and consistencies?
I think the thing to anchor on is, in the spectrum of verifiability, what you have said is the end on one side, which is like traditional RLHF, which is like, we will never fully verify this, and the learning of the model is mostly based on, like, a good model has training data that reflects multiple opinions. And a rabbit hole, but something I'm following now is, like, if you compare a model like Tülu to, for example, Llama Instruct, which is trained with a lot of human data on the same base model. If you look at different like downstream reward models and types of robustness, I think there's definitely signs, for example, that Llama is trained extensively on this human data that has this sort of, I wouldn't necessarily say disagreement, but there's just like an inherent noise to it, where the preference data on Tülu is synthetic. So this is mostly a thing that I'm following that is interesting as an aside to the answer, which is there are definitely domains that you can't verify, but it's mostly just acknowledging that things like facts are slightly more verifiable than things that are open-ended, and trying to like really be in control of that
Well,
distribution.
just a quick follow-up. Thank you for that. But does it mean that reinforcement learning is a dead end for non-verifiable problems?
There's a lot of the thing is it's like the optimizer has still been used with RLHF. It's still the same RL optimization function. So I don't think it's a dead end. I think that there's a long stand of research whether or not you train directly on the preferences with these like DPO or like algorithms versus RL. And I think that RL being used more in general will help RL be used more in that situation. But that's kind of like a bigger post-training, how do you make high-level decisions on your training recipe thing than specific to the like RL stuff.
Right. Thank you.
Yeah.
There was a question, and then I'll go to Ryan. But first, the Q&A. For Tülu, are there any plans of extending with more multi-turn preference data sets? And if so, which data sets are you looking at, given the relative sparsity of multi-turn preference data sets?
We're making our own as well, but also as like I'm just this week has been working on like filtering all of like help steer and LMSys's released data sets for multi-turn. I don't think there's a lot. I think if you look at those data sets and you filter for ones that are like over 3,000 tokens in length, which can be across turns, it's really that there's only like 1,500 examples. So there's not a lot in terms of that, but also working on synthetic data methods to add turns to data. Or you can also do things like for certain, we don't know which domains work with this, but for some domains, you can just stack queries that are unrelated. So like if you use ChatGPT, you just change the topic. We can do that in the training data, which is we just have another query that's it's stacked as a multi-turn query that is kind of off topic. But yes, we're working on it because we have seen that that's one of the things that like the usability of Tülu is much lower than the usability of Llama if the scores on our eval suites are similar.
Thanks. Yeah, I guess if that person has like follow-ups, they can unmute later too. But yeah, Ryan, do you want to unmute and ask your question?
Yeah, thank you so much, Nathan. It was a wonderful talk. I also saw a lot of applications before. I used to be at JPL as a machine learning scientist working RL, but most of the cases we had difficulty defining this reward function, especially when the data is multimodal system. So what you showed so far, I don't think it was more like a vision side and multimodal system. So what's your vision in terms of bringing, multimodal like input and output, and that's the more need, I think, in real world applications and spatial intelligence.
Yeah, I don't have a lot of experience here. I think there's another question in the chat of like relations between these and robotics. I think there's some opinions that I draw on, which is like if you're just doing like image classification, I think that's one thing, which is like I don't think you're going to gain from RL. I think like classifying the language models can also be very good, but it's more of integrating the multimodal stream in terms of tasks that we were already solving. So like an operator agent, I think that it's like if you add the screen on top of some other data, you could think about adding the information. But I mostly just welcome people that are working this area to teach me. I think that as you go from something like math or code, all of these multimodal or tool use or agent RL problems seem far harder, but the impact in terms of real world use cases seems far higher. So it's like just a higher risk, higher reward. I don't know. If you want to frame your question again, I gave mostly a non-answer, but I'm interested in the area.
So the example that we have, let's say one of these examples is satellite remote sensing. And we need to kind of identify the areas like a fire, like where the fire is, how it propagates, right? In some sort of like a reasoning too that we need to bring, and also the physics-based models. So we need to combine the physics-based model with these LLMs. That's one application that we have we're working on. But the problem what we do see is this vision language model, the validation is not easy to do. So what terms of validation you can think about, or how we can list that, like cast our reward function in the scenarios that you have multiple, you have a physics-based model as well as the multimodal systems.
Yeah, I think this is very much on like it seems similar to the spectrum and verifiability projects that we have going, which is breaking the reward into intermediate parts or like towards subparts that you can conceivably do better at. And like, for example, we're trying to build like an open model in a pipeline at AI2 for a semantic scholar project that can be as good as a closed model. And we have to like build an evaluator that is really good at understanding the tasks that we're trying to solve. And for example, you might need to like build rubrics and collect a bunch of LLM as a judge data, and then like train a classifier based off of that rubric, which are like the classifier is definitely not a function, so it's a softer reward. But trying to train a model that's like really, really specific to understanding the tasks that we had, which I openly don't know how easy this will be relative to the kind of RLVR math code stuff. But that's the kind of the approach that we're taking, is we like break down the problem and try to get as reliable of a signal as we can on our sub problem, with the understanding that there's uncertainty based on like how good that signal is.
Thank you.
So Yolanda had put her question in the chat. I think you recognized, but if there's anything else she wants to, or you wanted to add about that, or she wanted to unmute and talk about.
I think you answered it. Thank you.
Yeah, I think it's people like there's my contemporizing on it. I don't know, I'm missing the exact word. Is that I think a lot of the intelligence explosion things that people are now pointing to RL as a potential path to like keep climbing on all of these domains, is that a lot of the domains that people are going to try to move the RL for language model stuff are going to start looking a lot more like RL for robotics, or language models for robotics, where it's like if you're trying to do any sort of biology or science or anything like deep simulators that are quirky, it's going to start getting much more like these older RL problems, and the progress is going to be much more hands-on and tricky compared to, oh, math number go up or code is right or wrong. I think, and that's something that I want to keep thinking about, because it's really remarkable that people are like, oh, RL is the new paradigm that's going to help us get to whatever your favorite definition of AGI or super intelligence in the next 2 years. But I just don't like, it's just like people have tried these problems and there's slow results in like generalizing robotics with large models, but they're not like low-level controllers, and they have all sorts of abstractions built into them. So I'm very curious to see how that evolves, and I think people that did robotics are in a good place to understand the challenges of doing these problems.
Thank you.
There's like a minute left if anyone has like any quick questions.
Hi, Nathan. I have a question. Currently, the reinforcement fattening in large model is most focused on the mathematics and the code or other traditional reinforced learning tasks such as gaming. So I'm wondering whether it's other tasks that reinforcement tuning can use for. I heard you mention that IO for tools. Could you give me some detail?
We haven't fully set it up. I think the tools example is like, does the model choose the right tool at the right time? I think I don't know if this is how people actually do this, but the type of thing would be, how do you train the model to know that it needs to use search for a factual query or something like this? Or how do you train the model to know that it needs to use code to verify a math problem that you put in? Which is like, you reward the model for that. The tool is a token that the model outputs. So it's like in the search case, it's like you're essentially trying to have the model build the attribution from factual question to needing to use search. And I think that's like a somewhat reasonable example, which is then you do RL and it knows to generate that token at the right time. the more complicated things that people are actually doing is when you have multiple tools that you can call at any time, and you're trying to do multiple tool calls in a sequence to achieve some kind of somewhat unclear goal. And I think you kind of bridge that gap, but it's like early research at AI too that I don't 100% know how it is done, and a lot of hypothesizing on like what OpenAI means when they use RL for deep research or something like this.
Thank you.
So I think we'll end it to give people like lunch break in between, and Nathan will talk with people after that too. Maybe if people have additional questions, they can reach out to Nathan, but thanks everyone for coming, and thanks Nathan again for speaking with us. It was really interesting. So
Yeah,
thank
sounds
you.
good. We'll see you guys soon.